Listen to Dr. Ben Henley discuss both past records and current models and what this science tells us we need to do about the climate emergency.
Ben has worked in both academia and industry investigating hydroclimatic variability and water resource system performance, undertaking hydrological modelling underpinning major water planning decisions. Ben lectures in paleoclimatology, future climates and climate change, energy and human security. His research includes advances in the areas of decadal climate variability, the El Niño Southern Oscillation, the climate of the past 2,000 years, the evaluation of climate models, hydrological modelling. He was a recipient of Engineers Australia GN Alexander Medal in 2016, and he won a Young Tall Poppy Award in 2020. I hope that's a native pop. He is an editor of the international journal Wires, Climate Change, a chief investigator on the $36 million project Securing Antarctica's Environmental Future, and a contributing author to the most recent of IPCC's sixth assessment report in 2021, the science of which underpins deliberations at the COP26 conference in Glasgow. He's also our son. Ben.
and a plant lover, you could add. Well, thanks, Dad, and everyone. So I would like to speak to you all today about the climate emergency, but kind of from a different point of view that perhaps you've thought about before, really about how the records of the past and the models of the future can show us what we need to do. This kind of covers some of my the work that I've done. As a bit of an introduction, I like to sort of just put us in a bit of context here, and I think probably most of you need no reminding about this image that was quite famous some decades ago, but I'd just like to bring it up because I think it's puts us all in a bit of context. So I'm going to read a quote for you at the moment. We succeeded in taking that picture from deep space, and if you look at it, you can see it's a dot. That's here. That's home. That's us. On it's everyone you've ever heard of, every human being who ever lived out their lives, the aggregate of all our joys and sufferings, thousands of confident religions, ideologies and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilizations, every king and peasant, every young couple in love, every hopeful child, every mother and father, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there on a mote of dust suspended in a sunbeam. So, of course, that's our Earth taken from deep space, and it just, I guess, gives us a little bit of context. Now, I'll continue with a few more context shots. So I live in Melbourne now, but as they say, you can take the boy out of Newcastle. But Newcastle still feels like home. And you need no reminder about that image, which is basically every climate talk from anyone from Newcastle has to put that shot up. But I've seen a few changes, of course, in my short life. And my grandfather was actually the draftsman who drew up and many of the plans for the coal-fired power stations. And his grandson is now a climate scientist. And in our lifetimes, we saw the changes that are going on, not fast enough, but that are taking place. When I was about 4 years old, I probably even younger, Dad will probably tell us, I knew and could spout, I was like a little parrot, and I could tell you that this was Cryptandra scortekinii when I was about 3 or 4 years old. I did a few other things. I actually, when I was 7 years old, I won the SGAP, as it was at the time, colouring in competition. I won this book. I've got it here. I've got it right here to prove it. It says, presented to Benjamin Henley, first prize infants colouring in competition, Newcastle SGAP Spectacular 1989, Gloria Booth, president. So I have the proof, and I still treasure this book to the day. It kind of formed a lot of my worldview, I guess, in a broad sense. And that was me when I was about 8. So Dad sent me that photo. A few other books shaped my views, probably like many of you. Perhaps you read Tim Flannery's book, The Weathermakers, that sort of really woke Australia up, I think. And I think we have to give it to Tim Flannery for I guess, making us wake up and see this as a serious issue that Australia had to take very seriously. I wrote a not so interesting book of my own when I was about 30, and with a whole bunch of statistics and stuff. But really, at the end of the day, it was just my P plates for becoming a scientist. And often people are interested in how, your sort of winding path to how you got there. So I've put a few things here which you can kind of see. I was at Hunterwater for a little while, and then had a couple of postdocs at Melbourne Uni, and then now I'm a lecturer at Monash Uni. So that's kind of getting towards being enough about me. I've been really lucky to be a scientist at Melbourne and Monash Unis. And people take a lot of interest in our work, particularly in water supply issues and climate change and so on. But most of the time, we're actually doing research and teaching, and that little sort of 20% tack on the end is media and communication stuff, which where the public sees us, and that's where you sort of, I guess, try to have your impact. But at the end of the day, we do spend a hell of a lot of time teaching students and developing units and doing our research. So that's kind of my broad and quick background. But to me, science is really just about the following things. It's about having a curiosity and a wonder, and developing a fascination in what we what we see. Then forming a set of questions and hypotheses, searching for evidence, finding what we feel is the truth behind what we see, and then essentially, in order to make a better world in many ways. So that's kind of my kind of summary of what we're really here to do. And we're thinking, of course, about the complex system that is the Earth climate system. And you only have to look at a satellite photo taken just a few days ago of the Earth's system, the surface in our region, just see the complex weather patterns, the complex cloud forms, to see that this is a really complex and difficult thing to actually model. And that's, of course, what we do in climate science. And we break it down into a much simpler system in a grid. We think about all of the interactions between parts of the system, and you can see some of those shown in this. Breaking it down even further, you can kind of think of the climate system as 5 key parts. So you've got the atmosphere, you've got the land surface vegetation, and the land surface itself. You've got the ocean and the ice, the cryosphere. And then you've got a whole bunch of possible external changes, so things like long, slow changes in the tectonics. You've got changes in the Earth's orbit and changes in the sun strength. But then there's changes inside the Earth system itself, changes in the atmosphere, in ice, vegetation, and the ocean and land surface. So we kind of break our models up into these different kind of zones, you might think. Is someone sort of rattling around that might be able to mute themselves? But this set of complex equations, it might not look beautiful to many people, but actually this is the beautiful maths that goes into these massive climate models. And at the end of the day, it's quite an amazing thing that you can take a simple physical principle like Newton's second law or that mass is conserved, and you can divide a grid of the ocean up, and you can basically solve the problem of how the Earth's climate is evolving and how it will change. And how do we actually do that? Well, it's a massive challenge, and we do it on these huge computers. So you might imagine that these computers are maybe the size of a room or something, but they're actually the size of a massive building. And this has actually been, there's an even bigger computer now, Gardi, but the cooling these huge machines is a massive engineering challenge in itself. And we can start to understand with those climate models why we see the changes that we do. And just as a hint of where we expect to go in Australia with our rainfall changes, which is of course absolutely fundamental to how plants are going to respond, is broadly speaking, changes in precipitation that we'll see drier weather, drier averages essentially in the southern part of the country, and perhaps a wetting of the north and probably the northwest, particularly in the warmer season, but cool season drying in the south. And it's unfortunately a bit of a mixed message on the coast of New South Wales. Probably slightly increased variability and more intense rainfall, but it's difficult to pin down exactly what's going to happen in central, eastern New South Wales, and that's kind of because a lot of the models agree on certain regions of the world. So you can see in these parts of the world at 4 degrees warming, the models have pretty strong agreement in some regions of drying, particularly Mediterranean drying, southeast US, but other areas of increased rainfall, particularly in the tropics, we're going to see increases in rainfall, and also the high latitudes. But there's some regions where there's not so much agreement. So that's kind of the broad picture of rainfall. But to step back a little bit further, we're getting hotter, and we're getting hotter fast. And I don't think anyone here needs reminding about this time series from 1900 to the near present. And in terms of pre-industrial climate, we've reached now around about the 1.1 degrees centigrade relative to pre-industrial, which is about a degree in terms of the relative to the 1900 to 2000 level. So the question is, well, what happened before this, and what actually caused the Earth to get hotter? Well, we are pretty sure we know about that, but you may not have had too much of a look at the temperature of the Earth in the last 500 million years, or perhaps the last sort of 65 million years. And there's a huge range of temperatures, a vast array of variability in the climate system over those millions of years. And the study of paleoclimatology is really trying to understand what drove those changes, what really was the driving force behind those changes. So here we are in the present here, and we're looking back in this first bit of stable period here that we get to until about 12,000 years ago is called the Holocene. It's pretty stable, and that's the time when humans were developing our agriculture and basically working out that we wanted to be in civilizations, in communities, and basically developing our agriculture to facilitate that. But prior to that, and since about 25,000 years ago, there was this LGM, the last glacial maximum, which was a period of much colder temperatures, and there were huge ice sheets over large parts of the northern hemisphere. Prior to that, there was this big up-down kind of jagged set of glacial, interglacial periods, which we'll talk about soon. And then prior to about 1 million years ago, you saw this slow increase as you're going back in time, but if you're going forward, a decrease all the way up through to what's called the Paleocene-Eocene thermal maximum, which was something like 15 degrees warmer on a global average. And over the course of these millions of years, there were huge changes in, of course, the whole evolution of life on Earth. So we as a world, not humans, but this planet has experienced huge change. The question is, do we really want to be there at the moment? Do we really want to be driving this scale of change? Because looking back, you can see this is the current, now adding the future scenarios onto this. The changes that we are actually talking about in the next just 100 or 200 years are on the scale of the millions or tens of millions of years change that we've seen over this time frame. So we are talking about absolutely massive changes to the climate system and every living thing that depends on it. Where are we headed? Well, that's a bit up to us. And as you can imagine, in the climate system, there's lots of complex feedbacks. But what do we mean by feedbacks? And maybe you're familiar with the idea of a microphone and put a speaker in front of the microphone, you get this feedback. Well, that is a kind of feedback. That's a positive feedback. Another positive feedback is when you get melting of ice, and particularly sea ice is really good at this. You get a reduction in the albedo, or the sort of reflectivity, I guess, of the surface. So not as much of that incoming solar radiation is being reflected. It's actually being absorbed by that darker surface, which is replaced by which has then replaced the white sea ice. So you're getting a reduction of that reflected light. So that's sort of an issue. That's a serious positive feedback that we're pretty worried about. There are negative feedbacks and positive feedbacks, and climate models try and put all of that together in one place and try and sort of figure out what the final solution is going to be. But just to have a bit of a, I guess this is the sort of maybe the sort of lecture part of this talk. We have experienced huge change in the past, and again, I'm plotting temperature here, or a delta O 18 record, which is kind of a proxy for ice sheet extent. And you can see as you go back through the millions of years, this really has changed massively. And so over like the tectonic scales, things like chemical weathering is an interaction between the solid Earth and the atmosphere that happens on really long time scales. And you get more weathering when you have basically higher temperature, which effectively reduces the CO2 over really long timescales. So it's a bit like a thermostat. It's hypothesized to keep the Earth inside a reasonable range. We are throwing that completely out of whack with what we're doing at the moment on a very fast time frame. But plate tectonics on those millions of years timescales have a real impact. They change how the heat is distributed around the world. They change where the boundaries, where the sort of gaps in where oceans can flow through, and they can change those big cycles. So the solid Earth's a huge reservoir, but there's actually a really slow exchange with the atmosphere. But those huge exchanges have happened in the past. Things like the closure or the opening of the Drake's Passage, which is that little gap between South America and the tail, or the peninsula of Antarctica, that didn't used to be open. When it opened, it allowed for the circumpolar current to kind of cut Antarctica off and allowed the big ice sheet to build up on Antarctica, which of course then gives more reflective area and more, more of the solar radiation is reflected back to space. And you can see when Antarctic ice sheets came into play was right about the same time as this opening of Drake's Passage. So that kind of shows you, and there's lots of other examples, but that kind of shows you that tectonics does play a role on these really long timescales. If we go down into the timescales now, we're thinking about hundreds of thousands of years. There's things that happen on orbital timescales. So these are things like what's called eccentricity, obliquity, and precession, the so-called Milankovitch cycles. And these essentially are ever so slight changes in the way the Earth is oriented relative to the sun, and things like eccentricity being how elliptical the orbit of the Earth is. So is it slightly more elliptical or a bit more circular? Obliquity is the tilt of the Earth. So that you can imagine that affects the seasons quite a lot. And precession is kind of a wobble on the Earth's orbit. Each of these happen at a different characteristic cycle, and they kind of have lots of interesting impacts on the Earth's climate over those tens and hundreds of thousands of years. So they affect things like the ice extent, the atmospheric greenhouse gases, and sea level. So at the last glacial maximum, you actually had sea levels 120 meters lower. So, there was land between large parts where you didn't see land. You don't see land today. Affected things like monsoons and so on. So these were immense ice sheets that we saw during the last glacial maximum. And I've got a few more sort of stats here, but it was a hell of a lot colder, actually, just 20-odd thousand years ago. It was about 4 to 7 degrees colder. The sea level was much lower, and there were these massive ice sheets built up over particularly the northern hemisphere, up to 3 kilometers thick. And the land in those regions is still rebounding from being, basically squashed under this massive layer of ice for many tens of thousands of years. Summer insolation at 10,000 years ago was at a maximum. So this is sort of how we know what sort of drove this is those slow changes in these things called Milankovitch cycles, the obliquity and the precession, basically slight changes in the orbits of the Earth relative to the sun actually drove that ice sheet melt. And then we had a little feedback kick in where greenhouse gases rose because of primarily from release from the oceans, which then kicked that warming off, and that's how we entered and there's a few other parts of this story called millennial oscillations and so on. But basically, that Pleistocene period of lots of glacial and interglacials gave way to this lovely, stable, warm Holocene, which we humans took great advantage of with our agriculture. So that's a bit of a story of the last few hundred thousands of years in a few minutes. But how do we actually know all of that? Well, enter the miraculous and amazing world of proxies and paleoclimate proxies. So things like ice cores, which you'd be reasonably familiar with, tree ring analysis or dendrochronology, coral analysis, where we look at the geochemistry, particularly of corals, and take cores of them. Also, over long time scales, drilling cores into the marine environment, into the sediment, and extracting little bugs that lived millions of years ago, and basically measuring the chemistry of their shells, among other things. And a similar thing can be done in lake systems. So you have lake sediments. And on top of that, you have some early historical human records, which we can get at as well. So this is kind of how we know all this. And each of these records has an interesting and different part to play in sort of putting all that whole picture together. So you'd be familiar with ice cores and capturing the gas out of those ice cores and dating the age of that, and therefore having a sense and having a record of what the CO2 concentration is, for example, in the past. And a few years ago, I was really lucky to go to the University of Bern and have a play around have a look really at their pretty amazing lab. And this is Hubertus Fischer, who's one of the world's top scientists in ice cores, and he just standing there and just sort of gives me a piece of ice and says, "Oh, that's about 10,000 years old. That's about 20,000 years old, and don't melt it, by the way." So that was pretty fun, and they're really amazing places where they're really just developing the instruments in order to make the measurements just on, as things progress. And we've got some really great labs here in Australia, particularly at CSIRO. And many of my colleagues work on corals, and this is some of our colleagues drilling a core on Christmas Island. And of course, you might sort of wonder, does that hurt the coral? Well, no. There's, they're pretty resilient, and you put a little plug over the top of that to make sure that the coral isn't, damaged in any way, and the living surface is kind of protected. But it's not an easy thing actually drilling a coral core and getting that back to the surface, and then measuring, and then basically trying to date those records. And so a few of my colleagues work closely on this kind of thing. And we can also take X-rays of the coral surface to look at the banding. A little bit like tree rings, corals sometimes have this banding, which we can use to date, and we can look at the density and the luminosity, the luminescence of the bands. It can tell us about the sediment in the water at the time the coral was formed. Also, dendrochronology plays a key role, and the science of tree rings. And you can see how we actually go about getting these cores. So here's a friend of mine when I was on a field trip in the Czech Republic a couple of years ago, taking a core. I think this was one of Judith's first trees she'd done. But she's showing you how we do it. And essentially it's this corer, which you drill a very narrow core right into the tree. You extract that core, and I'll go to the next shot. And what it allows you to do is to pull out this very thin core, which the tree quickly recovers from this damage. There's a few very small number of instances where it could do some damage to the tree, but overall this is very safe to do. And you can basically extract this core and sand it down on a flat sort of plinth. And then you can see the rings pop up really clearly, and then measure those rings under a scan or under a microscope. So you have this lovely core come out all the way to the center of the tree, and you don't have to kill the tree. So that's good news. But all of this information can be sort of brought together, and I've been lucky to be part of a few international efforts to sort of bring all of this paleoclimate information together. And this is a graph I just made a couple of weeks ago of atmospheric CO2 records from ice cores, and also global temperature as using a deuterium record as a proxy for global temperature. And you can see that close relationship between atmospheric CO2 and global temperature, and just how in the last 800,000 years, the global temperature anomaly really hasn't varied that much compared to what we're talking about into the future, in terms of a warming scenario. And also CO2, the orange line there, hasn't gone above about 300 parts per million, perhaps a couple of times come close, but 300 parts per million, we exceeded that, decades ago, and we're actually at 415 parts per million right now, or so. So it's a pretty worrying sign on those long-term trends. And a couple of years ago, we set about reconstructing the temperature of the Earth for the last 2,000 years. Basically, following on from what you might have heard is the hockey stick and the climate wars that Mike Mann talked about. Mike has a new book, which I would recommend. It's a really good one, talking more about the agency and the new climate war, so the urgency and the agency of the issue. But to look at global temperature over that 2,000-year time frame, we have a lot of different proxies. So you can see things like corals and glacial ice, hybrids, lake sediments, a whole bunch of things feeding in. This is records from all over the world. And if you put them all together in a framework that reconstructs temperature, you can then start to see the patterns of the past. So here's a bit of detail about those records if you're interested. So that was 2017, huge global effort to put that data together. The big question is, did we see a new hockey stick after Mike Mann's work in the late 90s? Well, the answer is, yeah, pretty much. You see this sort of fairly stable period in the early first, in the first millennium, and then a gradual decline in that second millennium, and before you see this very sharp rise when the Industrial Revolution kicked off. And lo and behold, it has a really clear relationship and clear match to that broad pattern of CO2 increase that really picked up from about the 1850s onwards. And so these dark lines here are from instrumental data sets, from measurements of the surface, from Argo floats and land observations. This is the instrumental. This dark line here is the instrumental record from Mauna Loa in the middle of the Pacific in Hawaii, and it aligns really closely with these measurements of CO2 from an ice core in Law Dome in Antarctica from the Australian missions down there. So you can see that instrumental data is really accurately, the ice core data is really accurately picking up the tail of that instrumental record. And you can see that that prior to about 1850 or so, there was never in the last 2,000 years CO2 levels at that level. So it's a real concern what we've got in our hands at the moment. And I guess that I like to sort of get to that context, when you're thinking about these things. And a couple of weeks ago, I had a strange email come into my inbox, and everyone gets weird emails and messages. There's been all kinds of hoaxes going around at the moment, but one it really just sort of intrigued me at the time. This woman was proposing, was sort of saying that she was a princess of Belgium, and she wanted me to send her some data and some plots and things. And I just thought, oh, what is this? This sounds a bit strange. And lo and behold, she really was a princess of Belgium, and she really did want some plots. And actually, this plot you see is including, as well as the one a couple of slides back, has just now, I think in the last couple of days, ended up in this journal, in this weekly news mag. And her name is Esmeralda. You can look her up, Princess Esmeralda of Belgium. My high school French is pretty rusty, so I can't read the whole article and understand it, but I get the sense of it. And there's my little plots sort of shoved off to the side there, but they are there. So that was kind of fun to be helping with that a bit. We've done some other things apart from reconstructing just global temperature. We've also tried to ask the question, well, can we use the coral records in the tropical Pacific? And each of these dots is a different coral record that we have, to try to understand whether El Nino is changing. And so some work, there's kind of been identified these two types of El Nino. There's the Central Pacific El Nino and the Eastern Pacific El Nino. So this one here is the Eastern Pacific, where you have like a lot of warming in that Eastern Pacific, and the Central Pacific, where you have sort of more of the warming in the Central Pacific, right? And the Eastern Pacific is actually relatively cool, but both of them are El Ninos. And we produced this lovely study, or my PhD student, Mandy, produced this great study, which kind of showed fairly clearly that the ratio of Central Pacific to Eastern Pacific El Ninos is changing over this, compared to the 400 years of the past. And so we seem to be seeing a lot more Central Pacific El Ninos. And that could mean a lot for Australia, because the way Australian rainfall responds depends on that Central and Eastern Pacific El Nino. So that's sort of something else we can get from these corals. But again, stepping back to the bigger picture, one very nice question that a colleague of ours in Paleo has asked when they put all of this data onto the one figure. So here we are in the present, looking back thousands of years before present, so this is 500,000 years, 1 million years, 1.5. Go back in the past, we've got different kinds of proxies. So here's that up-down sawtooth Pleistocene record from the ice cores in red. The blue dots are marine sediment records, and different sets of marine sediment records. And you have to go back millions of years to, more than 2 million years into the past to see atmospheric CO2 levels that were even close to what they are today. And these future scenarios are basically where we could head, depending on what the choice of the world's leaders is. And so I guess another thing to point out on this graph is, well, actually, anatomically modern Homo sapiens only arrived about there. So our entire species hasn't experienced anything like what we are proposing to do. And the good question to ask is really, well, is Earth the best place for this kind of experiment? We know we're going to be up for more extreme events. Many of these can be attributed to climate change, and particularly the heat events. We're already seeing some really big changes in some of these extreme events, and particularly temperature-related events. So you're probably quite aware of the serious nature of rising temperatures and more extreme heat waves. We're going to see a lot more marine heat waves, and coral bleaching is certainly something, unfortunately and tragically for the Great Barrier Reef, that we'll see more of into the future. We'll see changes to precipitation patterns that are more difficult to pin down in terms of precisely how that will play out. Rainfall is hard to simulate, but some of those broader patterns that I talked about earlier are certainly what we expect. We do expect droughts to be hotter, and the drier regions are likely to get drier, and particularly southern Australia, the Mediterranean, places like that. And the tropics will likely get wetter, and we'll likely see more intense rainfall events. Tropical cyclones, some regions they'll get stronger. We may actually see fewer tropical cyclones, but the ones that we do see will be more intense. The Arctic is going to become ice-free, I think, is pretty much well established. We're going to see mass loss in West Antarctica that will lead to global sea level rise. We're going to see sea level rise of the order of, I would say, at least a metre, but the range is about 0.3 to 1.3 by the end of the century, and continuing far into the future, well beyond for many millennia, actually. And unfortunately, we're going to see most of the impacts in the poorer countries because they're less able to adapt. However, there is this thing called the Paris Agreement, which has, thanks to the small island states and our Pacific neighbours, actually has that 1.5 target built into the sort of aspirations of the Paris Agreement. Unfortunately, and we're seeing it play out this very week, where for some quite strange reason, really, we seem more preoccupied with talking about submarines than actually fixing this massive long-term problem, which has been a bit disappointing, actually. We're not doing enough, and I think every single scientist worth anything would tell you the same. If you look at the global warming levels, this is a map of the global warming levels that is consistent with what each country is actually saying they will do. And if you just take the average of what they're saying they're going to do, the red countries are basically proposing their nationally determined contribution in line with much higher levels of warming. They're basically saying we should go for 4 or 5 degrees of warming, and that'll be fine. So very few countries are really doing a superb job on any of this. And you can do your own plots on this parisequitycheck.org if you want. And perhaps things have got a little bit better since these two graphs that I've just shown. But the pledges and targets of the current Paris Agreement pledges and targets is going to get us in the range of around about 2.5 to 2.8, perhaps more like 2.7 or so degrees as a temperature rise. We really cannot afford that, because we know that above about 2 degrees, many of the sort of feedbacks in the climate system start to kick in, and particularly things like ice melting of large areas of Antarctica and Greenland will really get away on us, and we'll see massive sea level rise in the centuries to come. So 1.5 is where we need to be, and that means really, really rapid reductions in emissions very, very soon. There is hope. Some young people have really started to stick it to the decision makers, and I think they should be listened to. So I haven't spoken much about plants. I'm sorry about that, but I hope some of that was interesting to you, and I'm super happy to take any questions, or if you want to have a chat in any way about anything I've spoken to. Thank you.
If you enjoyed this video, why not subscribe and view other great content? New videos being added all the time.